So let's come to the second important plastic packaging technology, and that is a technology that is not only relevant for first level packaging but also for second level packaging. So that means to package not just the chip and the lead frame but a complete printed wiring board system, and so that means we will also have much bigger packages than in first level packaging. What we often need, especially in sensors, is a so-called cavity. That means the package must be hollow. The reason is that when we have a MEMS structure, that MEMS structure must be freely movable. We must not have some stiff material in contact with the surface, or we want to have access for some media. For instance, we want some gas to come to the surface, we want to have some pressure to come to the surface, and in that way cavities are often very important. And that means when we have such a package, we would like to start, for instance, with a lead frame. And around the lead frame we have a package, but the body of that package, which is made of plastic material, would be hollow. And in that way we would first produce the lead frame with this ring of plastic material. We would then, in the next step, mount and interconnect the chip, and finally we put on the lid on top and the bottom of our package, and in that way the package is closed. Of course, the alternative could be you try the molding with a cavity, but we must say until a few years ago, reactive transfer molding with epoxies was not possible when you wanted to make a cavity on the chip. And to that purpose, the so-called pre-molded plastic package was developed. As I said, pre-molded means we have a lead frame, we cover it with the plastic material. In the next step, so that's a pre-mold, and in the next step that pre-mold is assembled with a chip, and finally we close the whole thing. So on the other hand, it is important that such hollow packages will be low cost for large series production, and on the other hand we can have packages with a cavity. These can be made from hermetic materials like metal and ceramic, but these are very expensive. Another disadvantage is that epoxy molding compounds are only limited stable at high temperatures, and so people also were looking for alternative materials. And that's a reason which are in favor of so-called pre-molded plastic packages, and the main purpose of this and the main production process of such packages is injection molding. Please do not mix up injection molding with reactive transfer molding, because reactive transfer molding is made from a thermoset resin, while injection molding is made from a thermoplastic material which is melting in the process and which is solidified just due to cooling it down. How does it work? For instance, imagine we have a tool, so-called mold, and in that mold we insert our lead frame. So here that would be the lead frame. It is inserted, and we have a lead frame that is inserted into that molding tool. Here we have a machine. That machine has a screw, and on the back side the screw is with a grainy material of this plastic compound, and the screw transports the plastic material to the front. Here it is hot, here it is cold, here it is liquid, here it is solid. So this screw transports the material, and on the other hand, if we want to do the injection, we just push the piston here, and then this material will flow into, it will flow in here, and in that way we can fill our form. So when the form is filled, our part is more or less ready. Then this whole screw is retracted, and all of the parts are moved apart. So the mold is opened, the device will fall out or will be ejected by some ejection rods, and also this screw body here will be removed a little. And after that is accomplished, again we will feed such a lead frame. We will close all of this. The screw will rotate again, and then it will be pushed. And in that way, we have a continuous process of injection, opening, reloading, injection, opening, reloading. And that can be at a very high rate. Notice the molding time here is roughly 20 to 40 seconds, while in reactive transfer molding it is 1 minute to 2.5 minutes. So you could say that's 3 times faster than reactive transfer molding. And a factor of 3 is really a good argument to use such a different process. Here I can show you such a machine. That is a very small laboratory machine that already has a locking force of 500 kilonewton or 50 tons. It has 2 injection units. The screw is a relatively small screw with just 15 millimeter diameter. It's fully hydraulic driven. Here this unit is electrically heated, and also we need cooling water in the tool, which is inside here. In order to, after the cooling process, after the injection process, to have the package solidified. Injection molding can have very small parts which are injection molded, maybe only a few milligrams of weight, or it can go in some cases up to hundreds of kilograms of weight, which are processed in one shot here. If you have very small parts, you typically need to have many cavities, so you do many devices in parallel. Or if you do not want to make many, but they must be small, you can have a sacrificial cavity where you inject most of the material in the sacrificial cavity and throw away that material afterwards. Okay, that's such a machine. I must say, I know a company around here, and they have a production hall, and they have 100 of such machines standing and working there fully around the clock. Okay, now let's come to the packages. Here is the sensor package I was showing you initially. Here is the pre-molded lead frame with the plastic material. Here is a lead, and quite evidently it is that this was a pressure sensor. Here we have a hole to bring the pressure on the chip, and in that way we have three different parts. We have twice this part and once this part, and after the assembly these have to be united. In this case it's a so-called plastic leaded chip carrier 44, so we have 44 IOs on this. How do we make the complete assembly process? What's the process flow? So first of all, we produce a lead frame. Here you can already see we have cut this. Typically in such a lead frame we have 8 or 16 or even more individual devices, and these are brought onto the deposition machine, and first the adhesive is deposited, then the chip is picked and placed, and after that we go into a heating process. Typically it's a glue curing or sometimes a soldering process, but in most cases it's gluing. After that, we can go onto the wire bonding machine. The wire bond loops are formed from chip to the lead. And after that is finished, in most cases we do silicone potting. Even in pressure sensors, often we have a silicone on the membrane. Silicone is important against precipitation of water. So that is important to avoid. Under the dew point. So if moist air or moist gas becomes too cold, we will have condensation, we will see fog, and we will see wet surfaces. And wetting with water in electronics is not desired very much. To that purpose, often we have the silicone potting. And finally, we place the lid on top, and here we have some welding process. That can be different processes. It could be either by just heating. It also could be a laser. So we can say laser, ultrasound, and in that way we must form a tight seal, and then the package is almost finished. We had a ultrasonic welding machine. For that machine, you put on the lid. You have a tool. That tool is moved by ultrasound. The ultrasound can have a power of 250 to 550 watt. The typical frequency is 35 kilohertz. You will not be able to hear it, but maybe you feel it because it's a very high power. And within less than 1 second, this action of the ultrasound will lead to a local melting of the package. The amplitude also is very low. It's just 5 micrometers of vibration. And with that vibration, the whole package is deformed, for instance, by 0.3 millimeters. And another advantage of that process is that it's at room temperature. So it's a relatively cheap process. It's very efficient. But one of the advantages is it's a strong vibration. And in order to damp that vibration, it is also important to use that silicone gel on the device, because that gel is damping the vibration. For instance, you will not have a vibration of the bonding wires, and they will not be damaged by that process. Here you can see in these regions here, we will have a melting of the material. You can have a very proper sealing of the device. It is sealed well, but of course it's not hermetic because it's a plastic material. Also, there is one thing which is important for the material. We have the small gray dots. These dots are glass fibers which are embedded in the material, and they strengthen this material and they lower the CTE of this material. So we have already started to discuss the materials. There are mainly 3 or 4 materials which are important. I just want to show you several here. One is PBT. That's a low-cost material, very similar to the material from which we make Coca-Cola bottles. So it's polybutylene terephthalate. It's an ester. That's an ester group. That's a butylene group. And that's some phenolic ring. So in fact, these materials have 2 ester groups. That's the second ester group. These materials can be processed well in injection molding. They melt around, let's say, 250 degrees centigrade. And so that's a low-cost material. A material which is much more expensive, which also has much higher processing temperatures, is liquid crystal polymer. It again is an ester, as we see here from the ester group. In fact, it's not very much different from that PBT, just this butylene group is missing. But the more of these phenolic rings we have, the more stable this material is. And also these many phenolic rings lead to effect that this material is a little crystalline. This PBT is more amorphous, and this LCP is is crystallizing in the solid state. The third material I would like to mention here is polyphenylene sulfide. So that's just a phenolic ring with a sulfurous group. And what is always important is all of these are linear chains. That's different to thermoset resins, which make three-dimensional networks. Here we have just some kind of spaghetti code, and this enables us to melt this material. I forgot something. The fourth material is polyamide, abbreviation PA6, PA66. In former times, this was called nylon, which is a brand name by DuPont company. But there are many other polyamides now in the market. So what is important is, first of all, the injection molding temperature. So we must melt the material. And for the PBT, it's from 250 degrees centigrade on. For the LCP, it's roughly 100 degrees higher where it melts. And this PPS material melts a little below this LCP material. These high temperatures are also a reason why we will not be able to coat pre-assemblies directly with such plastic materials. We have tried that in former times, but these high temperatures always lead to damage of the chips and the lead frames, so that's not possible. And it means injection molding has always to be combined with pre-molding design. Okay, when we look at the properties, we can say the glass transition temperature of these materials typically is not so high, maybe 100 degrees centigrade or somewhat higher. Also, these materials have a relatively high CTE compared to molding compounds. For instance, for the PBT, it is 25 ppm per Kelvin. For the PPS, it's 14 ppm per Kelvin. And for the LCP, it is between 10 and 40 degree centigrade or ppm per degree. And that means this CTE, of course, has to be taken into account in the injection molding process, because we cool it from 300 degrees centigrade down to roughly 100 degrees centigrade. And that means we have lots of shrinkage. And if the shrinkage is different in different directions, what will be the effect? The effect will be that something which was round will become an egg when we have the different directions which are in parallel or in perpendicular direction. So that means making parts from such LCP material is not so simple, because you want to have a cube, let's say 1 centimeter in each direction, and in one direction it is 20 micrometers smaller than in the other direction. That would mean you have to rework your mold. Of course, the mold can always only be made larger, so you must first make one which is too small, then you measure it, you rework your mold, you do the molding process again, and so on, and that is quite time consuming. So that's the reason why injection molding is a very good process for mass production, but the initial costs or the general costs of having that process and operating it are very high. And that means in such processes we need high throughput and we need large series, and we want to produce hundreds of thousands of such devices. Now coming back to the material, some of the materials are very good when you regard water absorption. For instance, the LCP and the PPS are below 0.02 or 0.08%, so they hardly take up any water. That's good for electrical properties. And also these materials are inherently inflammable. The reason is that these materials already contain lots of oxygen in the ester groups or contain lots of sulfurous, and that makes them inflammable. You can burn them with additional energy, but they will not burn by themselves. Another property which is important is the dielectric constant or permittivity, which is roughly around 4, and that is similar to molding compounds, which also have roughly 4 as a permittivity. Another property is the dielectric loss factor, which is especially low in that PPS material. Some time ago I had a project, and in that project we were looking at different materials. Here at that time we were evaluating if we would like to introduce such a complete injection molding pre-molded process into production, and we had several criteria which we wanted to regard. First of all, we wanted to know how is the processing of the polymer? Is it easy to be processed? Is it hard to process it, especially in the injection molding? And here we thought the LCP would be very good, and also PPS and such materials would be quite good, or yes, as we have seen here, PPS. At that time we didn't regard PBT because that material was too cheap and not good enough. Another aspect when you want to do a lead frame based device is the adhesion against metals. We did lots of investigations. Unfortunately, the LCP, which can be processed well, doesn't adhere well to the metal. Then there is the question of soldering resilience. What does that mean? When you go into a soldering process with such a package, how will it come out? And some of the materials, they just melt, or they are crumpled, or they have popcorning effect or so. And that means only the very stable materials can survive soldering. Of course, you can solder with a soldering iron where the complete package is not heated, but we want to have mass soldering processes like running all of the board through an oven, and to that purpose it's important to have that, that material resilient against heat. Another property which is very much related to this is the temperature index. That means how much the material deforms under a small load at 180 degrees centigrade. Again, PEEK is a very excellent material, LCP is also good, and PPS also. How much moisture will it take up? Again, these materials are very good, but on the other hand, the PPS is a cheap material. Cheap means somewhere around kilogram at costs of few euros. For the PEEK, you rather talk about 100 euros per kilogram, and for the LCP, you are somewhere in between. So the PEEK, also for medical equipment, it is the optimum material, but you can only use it in applications where costs don't matter at all. Okay, here is such a package we designed and investigated for a pressure sensor, just as an example of such package. Another example is something for second level packaging. So here we can put in a complete printed wiring board. What is also interesting is we often already produce an interconnector socket where you can just put in a plug to interconnect it, for instance, to a cable set. And we can have mechanical structures, like in that case, it is a hole to screw the device up to some machinery, for instance. Okay, here it's still more complex. This cylindrical structure, it can take up something like an electrical motor. Yeah? So this is not only the housing for or package for electronic device, but it also has some mechatronic parts. And in that way, such devices can combine directly a structural and functional behavior. We can see in that way we can produce millions of devices per year at low costs. We have very many possibilities to design. We can also have multifunctionality. These packages can be temperature stable when we use the proper material. And one of the important factors is the glass fibers increasing the strength. But again, it's plastic materials, and some applications still require metal or ceramic materials. Also, the tightness against humidity is limited, or it requires cost-intensive additional sealing like silicone. Okay. Here, that is an example by the Bosch company. Bosch uses pre-molded packaging very much in MEMS devices for automotive applications. Here we have already seen it. That is a pre-molded package, for instance, from LCP or some similar material, or from PA66, having the ASIC, digital analog part, and the MEMS device. That's for rotational rates, that's just for acceleration, so it's smaller. And that's a standard device produced in millions first in the wafer fab and then in the packaging. The whole sensor comes into cars, but every car manufacturer has a different architecture, and the device is adapted to the car electronic architecture using such a printed wiring board assembly, and to that purpose we need second level assembly. Again, this is done with such a pre-molded package. Again, we combine structural parts and we combine an interconnector. So that's a technology which is still used in in tens of millions of numbers for automotive applications. Another example, again here, which I investigated together with a company. That's a company having the 100 injection molding machines. They produce, for instance, such a pressure sensor which is attached to a fuel pipe. So here comes the end or a T-junction of a pipe, and here we can measure directly the pressure. The pressure sensor is here. The complete electronic part is just on that printed wiring board. The ASIC cannot be seen here, but that means we have the combination of a cheap printed wiring board technology, of a MEMS technology. Here we have the glass body of this pressure transducer, and we have a large series production of injection molded parts. So finally, this printed wiring board is brought in here. So it's flipped in here, put in here. The lid is put on top. Of course, it must be interconnected. We can see here the holes for the interconnector, and so we have a very efficient construction. And again, the costs for such a device, they can just amount to few euros. Again, when we look at such complex parts, we must say it is still necessary we have some lead frame. Again, here we see the lead frame which is mounted into some injection molded part. That's even a very primitive design, because here the lead frame is mounted after the injection molding and it is riveted here. Such sockets, for instance, for light bulbs or similar applications are produced in large numbers, but putting together metals and plastics manually is always labor intensive, and for that reason, people were seeking to make it more efficient. And to that purpose, the so-called molded interconnect device was invented. Let me tell you what it is. A molded interconnect device is a device where the body of the package is still injection molded from a thermoplastic material. But here we have no lead frame. The metal interconnections are rather produced by metallization on the polymer. So that means the idea is not to use a lead frame or an additional metal structure, but to metallize the plastic after the injection molding process. In that way, some demonstrator designs were proven, so we can have a quite complex device. For instance, an advantage would be we have this complex body, injection mold, the chip is mounted. We make the wire bond connection to the metallization on this plastic body. This is coming along here, and we have the ASIC, for instance, also interconnected to that wiring conductor here by some wire bonding. Okay, that could be a very efficient design and a efficient technology, and that is so-called MID technology, Molded Interconnect Device. So it's a multifunctional device. As we can see, also a flow channel can be integrated, a pressure port or a tube interconnection can be accomplished. We have mechanical interfaces, of course, attaching it, and we can have conducting elements that are integral part of the housing. On the other hand, we could discuss, is such a design where the plastic is metallized directly, is it more effective than a design where the metal is formed as a lead frame, which is covered by injection molding, and where the circuitry is on the basis of a printed wiring board. So that's something you should be able to evaluate what is more efficient and what could be reasons for one or the other technology. Okay, now having this laser direct structuring technology, here you see a real injection molding machine. It's much bigger than the laboratory machine, and here the polymer is a laser activatable plastic material. That means if you direct a laser beam on that material, certain substances are released. In fact, it is some kind of very small metal crystals which are released, palladium crystals. And so you can write a trace which is not visible onto the plastic material. And when you, after the laser activation, have cleaned the surface of your device, you can put it into an electroless plating bath. That's some solution of first nickel and then gold, and you dip it in, then on the laser activated surfaces, nickel and gold are deposited. So we deposit metallization, and in that way we have conducting lines. What could be disadvantages when you have instead a printed wiring board? Maybe the lines are thicker and can carry more current. Also, I could imagine that that processes like wire bonding are not as easy on such electroless platings compared to platings on printed wiring boards or on lead frames. What is also possible, you can make a two-shot process. You can have a first shot from a material that is that cannot be metallized, and you have a second shot from a material that can be metallized. So you do not have this laser activation, but you just have two different materials. You go into the plating, and in the plating only the one part, as we can see it here, is laser plated. So first shot is platable, second shot is non-platable, insulating. And in that way, we can also make a certain package. After that, of course, we always have electrical test, inspection, before it can go to further assembly. Here is another example. The advantage of such parts is they integrate mechanical, fluidic, and electrical functions. For instance, that is an optical bench just produced by injection molding, metallizing. Here, for instance, a lens. Here, some sensor is mounted. We have a lens that can be mounted. We have some aperture on top. And all of these do not have to be precision aligned, but the precision is part of the injection molding process. So it just fits together, and in that way we can make precision parts assembled of many different elements, and in that way we can have a very efficient large series production of complex parts. So advantages are, this is valid for cost-sensitive and high-volume applications. We can reduce height and have a small footprint. 3D, in this case, is without additional costs. We have high-precision processes, and we have highly specific solutions at reasonable costs. Also, we have many options for design, and after that we can also do some overmolding going into a glob top or molding process. Interesting is here, for instance, that's a 3D magnetic sensor. For these sensors, it's very important that we have a very good alignment of the axis. And that alignment is a result of the precision which is part of this fabrication. That was a demonstrator. Strange thing is, shortly after this company had presented their packaging solution for such a 3D magnetic sensor, another company was showing a 3D magnetic sensor which has 3-dimensional capabilities on one chip. Of course, you could say such a 3D sensor here is better, especially sensitivity in all axes is better than on a 3D chip. On the other hand, a 3D chip is smaller, and that again shows us the everlasting war between hybrid integration and monolithic integration. Okay, again, here we have a roadmap. I have already shown it. Initially, it was relatively simple devices, just making the package body. Even the interconnector was separately made. Later on, we integrated mechanical parts, optical parts. Here again, we have the combination of printed wiring board and injection molded housing, while on the other hand, one of the trends was going to molded interconnect devices. On the other hand, we must say that replaces rather the printed wiring board. It doesn't yet replace the package itself. But it shows us packaging processes become more and more complex. Also, to distinguish between first-level packaging and second-level packaging is not so sensible, and when you have mechatronic solutions where you combine very many functions. Okay. I will not go through all of these comparisons in the tables. You can look it up for yourself. And in that way, we have seen 3 important technologies. One is the reactive transfer molding. It's important. It is thermoset materials. Second, we have the pre-molded packaging, which again uses a lead frame. And in order to get rid of the lead frame, the molded interconnect device technology has been developed. Okay? Thanks for your attention for today. See you.